Hi, my name is Reyne. I'm a lecturer from the University of Sydney, and I'll be one of the few who are giving you a hand with writing out some of these worked examples for some of the spectroscopy questions that you may be receiving or styles of questions you may see. Now, this is the first one that I'm recording, so there are a couple of times where I'll explain a little bit more than usual, but otherwise in my later videos, I'll be a bit quicker because hopefully you'll start at the top and you'll work your way downwards. Now I'm starting with sample B. I'm going to assume that you've seen Stephen's video in sample A, but if not, maybe check that out first before moving on to others. And the way that I like to approach this is to try and think of this in terms of a puzzle. So I look at each of the different parts and I kind of try and bring it all together at the end. So I'm going to just work my way through down, talking a little bit about the point of each of these pieces of evidence we have and what they kind of say. Now, first of all, we can see here our 3 tests, okay? And this is just a great little first thing to check. It's experimental evidence. This is a really good way to double check what we'll later start to try and interpret out of the different types of spectroscopy we look at. Now, first of all, for an unsaturation test, we're looking to see if there are any double or triple bonds present, and there are none. We don't see a change in color from the orange solution. We're looking at an oxidation test using acidified potassium dichromate. So here we're looking to see, is there anything that we can oxidize? Again, we see no reaction. So that tells us that there are no double, no triple. And here, there's no alcohols and no ketones or aldehydes. In fact, we wouldn't expect to see a ketone anyway, just because we can't oxidize a ketone. And then finally, we test for a carboxylic acid using sodium carbonate, and we see no bubbles. So that once again tells us that there's no carboxylic acid present. Now that's really good. It simplifies things a lot. So when we start to look at the data, we can piece that together. Now, I may not start with the IR, infrared spectroscopy, or the mass spectroscopy, because these to me are kind of often serve well as a confirmatory sort of piece of evidence. So sometimes it's a bit easier to start with our carbon and our proton NMR, and then we come back to these to think about, well, what functional groups may be present. So I'm going to scroll down past these first, come down to our carbon and our proton NMR, and start to pull these apart. Now the carbon tends to be an easier one. Straight away, we can see that we've got 1 peak, 2 peak, 3 peaks. Now that could mean that there are only 3 carbons present. If we think about the height of these peaks, or if we're able to calculate the area, that would be useful. But based off of this, we can maybe make an early assumption that there are 3 carbons present. And we can think about that a bit more when we start to come back to our mass spectrum, the mass spectrum that we've got here. So now when we come down to the proton NMR, here we can start to pull out a little bit of more deeper information that it's a little bit harder to kind of interpret. Now in this particular case, it kind of at first glance looks like we only have 2 peaks. So this idea that there's only 1 peak here and 2 peak here, but this is when we want to come down and have a look at this peak data table we've got below, which is telling us that there are actually 3 peaks. So in this particular case, it's probably better to kind of trust this peak data table, because at first glance, it's hard to really tell where the peaks are in this. They're kind of overlapping a little bit, and that'll make a bit more sense as well when we look at the final structure as to why that is. So based off of this, we actually have, if we label this A, B, and C, it's telling us that we've got A and B at this peak at about 130. And it's also telling us that we've got this peak C at about 0.9 in terms of their shift. Now we also then can kind of think about both the ratio and the number of peaks present there. And this information is really key when we think about a proton NMR, because it tells us a little bit about, for instance, the ratio says how many hydrogens in that environment. Whereas the number of peaks tells us how many neighboring hydrogens in the environments immediately around that. So from here, we can tell that we've got a certain number of protons, we've got a certain number of environments around the area. So we're kind of putting things together. Now at this stage, based on what we've seen, have a quick think and think, what kind of structure do you think this is? Because we haven't seen anything with a ppm that's really downfield. So we haven't seen any of the high ppm numbers down to 3, 4, 5, down to 10. We haven't seen that. And even with our carbon NMR, we can see that the ppm values for our carbon are relatively low. They're all kind of between 35 and about 15. So what's hopefully coming to mind is that this sounds like a hydrocarbon. It sounds like possibly just an alkane. We know that there's no double bonds present. Now at this stage, here is when we want to turn to then thinking about the mass spec and the IR to kind of confirm some of this information. Now you'll remember, right, that I said it looks like there's only 3 peaks in this carbon. And that could mean that there are 3 carbons, or there could be 6 carbons, or there could be more, multiples of 3. Based off of what the proton NMR said, so if we come down here to the ratio again, okay, it's suggesting that there are, for instance, 6 hydrogens at the 0.9 environment. Or if we look at either of the 1.3 or the 1.28, there are 4 hydrogens at each of those. Now that doesn't make sense if there's only 3 carbons. So we want to be open to the idea that there are more carbons present. A good way to check this is if we come to the mass spec. Now the mass spec is a hard one to interpret. And I would even flat out say that I wouldn't go too far beyond just thinking about the molecular ion. So we get the molecular ion by considering the highest peak that we observe. And the idea here is that we've just lost only 1 electron, and therefore we have this charged species, but it's effectively the same molar mass as the original compound. Now that's telling us that it's got a mass to charge ratio of 86. If we only have 3 carbons, that doesn't make sense. So what about if we double that? If we said, assume 6 carbons, right? That would tell us 6 times 12 would give us that 60, 72. And then if we say basis assumption, and this is often what you want to do, is just start at the most simplistic idea. Let's just assume that this is only an alkane. All right, so 6 carbons. If we think about the number of hydrogens that must be there with no double or triple bonds, which is going to be 2n plus 2. So if that's going to be 2 times 6 plus 2 equals 14 hydrogens present. And if there are 14 hydrogens present, that means that there's effectively a mass of 14 associated with that. So our final mass would be 86, and that would be for 6 carbons and for 14 hydrogens. Adds up to 86. Pretty compelling. So that kind of confirms for us that we've got the number of carbons right, we've got the number of protons right. We can kind of confirm that as well by looking at IR. At IR, we can see kind of this major peak here. And if we consult our table, what we kind of get from this is that it looks like it's probably going to be carbon to hydrogen being involved. I'm not sure if you go into stretches or bonds, but if you look up things online, you'll see that that's actually going to be the stretch, the carbon to hydrogen stretch. Whereas these peaks that we see here are likely going to be the carbon to hydrogen bend, okay? And then as a reminder, and I think Stephen mentioned this for sample A, we don't really deal with this. So this is the fingerprint. Oh, no, there's no E on the print. fingerprint zone, and it's very hard to interpret anything in them because it tends to be very messy. Here it's not too bad. And occasionally you can do some really fine-tuned analysis to try and pick out something important, but as we've confirmed, there are only carbons and hydrogens, so we're kind of happy with just picking out those two. A lot of what you see down in the fingerprint zone tends to be the carbon-carbon bonds. And because as your molecule gets larger and larger, there are more bends, more stretches possible, in which case it just becomes this mess of like a whole bunch of different peaks. So I'm feeling pretty good about this. The last thing we need to think about then is how is this arranged? And we have a really big clue if we come back down here to the fact that our carbon only has 3 peaks, but we know it's got 6 carbons. And the big clue here is that for that to work, it means that some of our carbon environments must be the same. So there must be 2 carbons with the same environments, and then another 2 with the same environments, and then another 2 with the same environments. So let's think, once again, we'll go with the simplest option for that. So we're going to go green. What if we just try hexane, for instance? Okay, so in hexane, we've got 6 carbons. They're all in a row. And the great thing here, right, is we can actually put a line through this and think of it as being mirrored. So anything that is on the one side is mirrored on the other side. So if we had an environment here, let's say this is 1, 2, 3 for our carbon environments, it must be the same on the other side. And that explains our carbon NMR. If we think about our proton NMR, we can also confirm some of that if we think about hexane. These really close peaks, 1.3 and 1.28, they're super close because they likely, I just get, maybe get a dark blue here, they're likely going to correspond with A and B. Because when you think about the de-shielding that occurs, so once again, I'm not sure how much depth you've gone into this, but the idea of de-shielding these zones, and therefore the more de-shielded they are, the more they move down, down in their shift. These will be very similar to one another. There's no factors that really differentiate them. The terminal carbons are different. They're not bridging, so they don't have to worry about 2 carbon-carbon bonds kind of sharing electron density between them. So the terminal carbons will then be our C peak as associated with this peak data table there. So putting that all together, we're left with this being hexane. If we wanted to, we could kind of come back for a final check. Would hexane work for all of these tests? Well, there's no double bond, there's nothing that can be oxidized, and there's no carboxylic acid. So I'm pretty convinced that that's hexane. Cheers.